Touching only one terminal of a direct current generator while standing on wet ground will not complete an electrical circuit, and therefore will not cause an electric shock. The human body needs to be in contact with both positive and negative terminals to create a conductive path for current to flow. Touching both terminals simultaneously will create a complete circuit, allowing current to flow through the operator's body. Wet skin has lower electrical resistance, increasing the likelihood of a more severe shock. The consequences can range from a painful but temporary shock to serious injury or death, depending on the amount of current flowing through the body. Direct current voltages at 52.5 volts direct current can pose significant safety hazards. Firstly, direct contact with both terminals can cause electric shock, which can lead to muscle spasms, pain, respiratory distress, burns, and heart failure. Secondly, high voltage direct current can cause internal tissue damage, including burns and nerve damage. Thirdly, if the contact is made through clothing that becomes electrically conductive, it can cause flash burns. Fourthly, in severe cases, electric shock can lead to cardiac arrest. Always prioritize safety when working with electrical equipment. There are several important safety precautions to keep in mind. Firstly, never touch the output terminals of a direct current generator while the engine is running. Secondly, ensure that the generator is properly grounded before operating. Thirdly, wear insulating gloves and shoes when handling the output terminals. Fourthly, keep the generator away from wet or damp areas. Fifthly, instruct all users on the safe operation of the generator. Sixthly, have a first aid kit readily available. Seventhly, if an electric shock occurs, seek immediate medical attention. The level of harm from electrical contact depends on several factors, including the voltage, the current, the duration of contact, and the path the current takes through the body. The resistance of the skin also plays a crucial role. Dry skin offers high resistance, while wet skin significantly reduces resistance, making the body more vulnerable to electric shock. Generally, voltages above 50 volts are considered hazardous. At 52.5 volts direct current, the potential for serious injury exists, especially if the skin is wet. Electrical current is measured in amps. Even a small amount of current can be dangerous. For example, a current of just 1 milliamp can be felt, while 10 milliamps can cause muscle contractions. A current of 100 milliamps can be fatal. The severity of an electric shock depends on the path the current takes through the body. If the current passes through the heart or lungs, it can be life-threatening. Symptoms of electric shock can range from mild tingling to severe burns and cardiac arrest. Muscle spasms, difficulty breathing, and loss of consciousness are also common. If someone experiences an electric shock, it's important to seek immediate medical attention. Even if the person appears to be fine, internal injuries may have occurred. When working with electrical equipment, it's essential to take precautions to prevent electric shock. Always disconnect the power source before working on electrical circuits. Use insulated tools and wear appropriate personal protective equipment, such as rubber gloves and safety glasses. Inspect electrical cords and equipment regularly for damage. Replace any damaged items immediately. Never overload electrical circuits. Overloading can cause wires to overheat and create a fire hazard. Be aware of the presence of water when working with electricity. Water is a good conductor of electricity, so it's important to keep electrical equipment away from water sources. Grounding is another important safety measure. Grounding provides a path for electrical current to flow safely to the ground in the event of a fault. Make sure that all electrical equipment is properly grounded. If you're not comfortable working with electricity, it's best to hire a qualified electrician. Electricians have the knowledge and experience to work safely with electricity. Regulations and standards provide guidelines for safe electrical practices. The National Electrical Code, or NEC, is a widely adopted standard for electrical installations. It provides requirements for wiring, grounding, and other electrical safety measures. Other organizations, such as the Occupational Safety and Health Administration, or OSHA, also provide guidelines for electrical safety in the workplace. Regular training is essential for anyone who works with electricity. Training should cover topics such as electrical hazards, safety procedures, and the use of personal protective equipment. By following safe electrical practices, you can reduce the risk of electric shock and other electrical hazards. Always be aware of the potential dangers of electricity and take precautions to protect yourself and others. When dealing with any electrical system, understanding the components and how they interact is crucial. A direct current or DC generator produces a unidirectional flow of electric charge. Unlike alternating current or AC generators, which reverse the direction of current flow periodically, DC generators maintain a constant polarity. The basic principle behind a DC generator's operation is electromagnetic induction. When a conductor, such as a wire, moves through a magnetic field, a voltage is induced in the conductor. This phenomenon is described by Faraday's law of electromagnetic induction, which states that the induced voltage is proportional to the rate of change of magnetic flux through the conductor. In a DC generator, a rotating armature, which consists of coils of wire, is placed within a stationary magnetic field. The magnetic field is typically created by permanent magnets or electromagnets. As the armature rotates, the conductors in the armature cut through the magnetic field lines, inducing a voltage in the conductors. The induced voltage in each conductor is an alternating voltage. However, a commutator is used to convert the alternating voltage into direct voltage. The commutator is a segmented ring that is connected to the armature windings. As the armature rotates, the commutator segments make contact with stationary brushes which are connected to the external circuit. The commutator reverses the connections to the armature windings at the point where the voltage is about to change polarity, resulting in a direct voltage output. DC generators are used in a variety of applications, including battery charging, powering electric motors, and providing backup power. They are commonly found in vehicles, portable generators, and industrial equipment. The output voltage of a DC generator can be controlled by adjusting the speed of the armature rotation or the strength of the magnetic field. Increasing the speed of rotation or the strength of the magnetic field will increase the output voltage. DC generators are typically rated in terms of their voltage and current output. The voltage rating indicates the maximum voltage that the generator can produce, while the current rating indicates the maximum current that the generator can deliver. It's important to choose a generator that is appropriately rated for the application. When working with a DC generator, it's important to follow safety precautions to prevent electric shock and other hazards. Always disconnect the generator from the power source before working on it. Use insulated tools and wear appropriate personal protective equipment. Inspect the generator regularly for damage and replace any damaged parts immediately. Never operate the generator in wet or damp conditions. Understanding the principles of DC generator operation and following safety precautions are essential for working safely and effectively with these devices. When evaluating the safety of electrical systems, it is essential to understand the concepts of voltage, current, and resistance. Voltage, measured in volts, is the electrical potential difference between 2 points in a circuit. It represents the force that drives electric charge through the circuit. Current, measured in amps, is the rate of flow of electric charge through a circuit. It represents the amount of charge that passes a given point in the circuit per unit of time. Resistance, measured in ohms, is the opposition to the flow of electric charge in a circuit. It represents the ability of a material to impede the flow of current. These three quantities are related by Ohm's law, which states that the voltage across a resistor is equal to the product of the current through the resistor and the resistance of the resistor. Mathematically, Ohm's law is expressed as V equals I times R, where V is the voltage, I is the current, and R is the resistance. Ohm's law is a fundamental principle in electrical engineering and is used to analyze and design electrical circuits. It can be used to calculate the current in a circuit if the voltage and resistance are known, or to calculate the voltage across a resistor if the current and resistance are known. When analyzing the safety of electrical systems, it is important to consider the potential for electric shock. The electric shock occurs when a person comes into contact with an electrical circuit and current flows through their body. The severity of electric shock depends on several factors, including the voltage, the current, the duration of contact, and the path of the current through the body. High voltage and high current are more likely to cause serious injury or death. The resistance of the human body also plays a role in the severity of electric shock. Dry skin has a high resistance, while wet skin has a low resistance. Therefore, wet skin increases the risk of electric shock. To prevent electric shock, it is important to take precautions such as using insulated tools, wearing appropriate personal protective equipment, and avoiding contact with energized electrical circuits. Grounding is another important safety measure that helps to prevent electric shock. Grounding provides a low resistance path for current to flow to ground in the event of a fault, reducing the risk of electric shock. Electrical safety is a critical concern in many industries and applications. Understanding the concepts of voltage, current, resistance, and Ohm's law is essential for ensuring the safe operation of electrical systems. By following safety precautions and using appropriate safety measures, the risk of electric shock can be significantly reduced. When dealing with electrical systems, understanding grounding and bonding is crucial for safety. Grounding is the process of connecting an electrical circuit or equipment to the earth, providing a low resistance path for current to flow in the event of a fault. Bonding is the process of connecting different metal parts of an electrical system together, creating an electrically conductive path between them. Grounding and bonding serve several important functions. Firstly, they help to prevent electric shock by providing a path for fault current to flow to ground, tripping a circuit breaker or fuse and disconnecting the power supply. Secondly, they help to reduce the risk of fire by preventing the buildup of static electricity and providing a path for fault current to flow, preventing overheating of electrical components. Thirdly, they help to improve the performance of electrical equipment by reducing electrical noise and interference. There are two main types of grounding systems. Firstly, equipment grounding, which involves connecting the metal parts of electrical equipment to ground. Secondly, system grounding, which involves connecting the neutral point of an electrical system to ground. Equipment grounding is typically achieved by connecting a grounding conductor to the metal enclosure of electrical equipment and then connecting the grounding conductor to the grounding electrode system. The grounding electrode system consists of one or more grounding electrodes, such as ground rods or ground plates, that are buried in the earth. System grounding is typically achieved by connecting the neutral point of a transformer or generator to the grounding electrode system. Bonding is typically achieved by connecting different metal parts of an electrical system together using bonding jumpers or bonding conductors. Bonding jumpers are short lengths of wire that are used to connect metal parts together, while bonding conductors are longer lengths of wire that are used to connect metal parts that are further apart. The National Electrical Code, or NEC, provides detailed requirements for grounding and bonding electrical systems. These requirements are designed to ensure the safety of people and property by preventing electric shock and fire hazards. It is important to follow the NEC requirements when installing and maintaining electrical systems. Grounding and bonding are essential safety measures that help to protect people and property from electrical hazards. By understanding the principles of grounding and bonding and following the NEC requirements, the risk of electric shock and fire can be significantly reduced. Electrical safety is a critical aspect of working with electrical systems. It is important to understand the potential hazards and take precautions to prevent accidents. One of the most common electrical hazards is electric shock, which can occur when a person comes into contact with an energized electrical circuit. The severity of electric shock depends on several factors, including the voltage, the current, the duration of contact, and the path of the current through the body. To prevent electric shock, it is important to take precautions such as using insulated tools, wearing appropriate personal protective equipment, and avoiding contact with energized electrical circuits. Another common electrical hazard is arc flash, which is a dangerous electrical explosion that can occur when there is a fault in an electrical system. Arc flash can cause severe burns, blindness, and even death. To prevent arc flash, it is important to follow safe work practices such as de-energizing equipment before working on it and wearing appropriate personal protective equipment such as arc-rated clothing and face shields. Electrical fires are another common electrical hazard. Electrical fires can be caused by a variety of factors, including overloaded circuits, faulty wiring, and damaged electrical equipment. To prevent electrical fires, it is important to inspect electrical equipment regularly for damage, avoid overloading circuits, and use appropriate fire extinguishers. The National Electrical Code, or NEC, provides detailed requirements for electrical safety. These requirements are designed to protect people and property from electrical hazards. It is important to follow the NEC requirements when installing and maintaining electrical systems. Electrical safety training is essential for anyone who works with electrical systems. Training should cover topics such as electrical hazards, safety procedures, and the use of personal protective equipment. By following safe work practices and taking appropriate precautions, the risk of electrical accidents can be significantly reduced. Electrical safety is a shared responsibility. Everyone who works with electrical systems has a responsibility to ensure their own safety and the safety of others. One aspect of generator safety is understanding chassis grounding. Chassis grounding refers to connecting the metal frame or chassis of an electrical device, such as a generator, to the earth. This connection provides a low resistance path for electrical current to flow in the event of a fault. The purpose of chassis grounding is to protect people from electric shock. If there is a fault in the generator and a metal part of the generator becomes energized, the chassis ground will provide a path for the current to flow to ground, tripping a circuit breaker or fuse and disconnecting the power supply. Without a chassis ground, a person could come into contact with the energized metal part and receive an electric shock. The National Electrical Code, or NEC, requires that all electrical equipment that is likely to become energized be grounded. This includes generators, motors, and other electrical devices. The NEC specifies the size and type of grounding conductors that must be used, as well as the methods for connecting the grounding conductors to the equipment and to the grounding electrode system. To ensure that a generator is properly grounded, it is important to follow the manufacturer's instructions and the requirements of the NEC. The grounding conductor should be connected to the generator's grounding lug, which is typically located on the frame of the generator. The grounding conductor should then be connected to the grounding electrode system, which consists of one or more grounding electrodes, such as ground rods or ground plates, that are buried in the earth. It is important to periodically inspect the grounding system to ensure that it is in good condition. The grounding conductor should be free of corrosion and damage, and the connections should be tight. If the grounding system is not in good condition, it should be repaired or replaced. Chassis grounding is an important safety measure that helps to protect people from electric shock. By following the manufacturer's instructions and the requirements of the NEC, you can ensure that your generator is properly grounded and that you are protected from electrical hazards. The information provided is for general guidance only and does not constitute professional advice. Always consult with a qualified electrician or other professional for specific advice related to your situation. The discussion of electrical safety hazards associated with direct current voltages around 52.5 volts direct current highlights several critical points. While touching only one terminal of a DC generator on wet ground might not complete a circuit, simultaneously touching both terminals can create a dangerous path through the body, especially with wet skin, leading to potential shocks, injuries, or even death. The specific hazards of direct current voltages at this level include electric shock leading to muscle spasms, respiratory distress, burns, and heart failure, potential tissue damage from internal burns and nerve damage, flash burns from conductive clothing, and in severe cases, cardiac arrest. The importance of safety precautions is paramount. Never touch the generator terminals while it is running. Ensure proper grounding, use insulated gear, avoid wet areas, educate users, keep a first aid kit accessible, and seek immediate medical help if a shock occurs. The severity of an electric shock depends on factors like voltage, current, contact duration, current path, and skin resistance, with wet skin significantly reducing resistance and increasing risk. Even low currents can be dangerous, and voltages above 50 volts are generally considered hazardous. When working with electrical equipment, always disconnect power before servicing. Use insulated tools and personal protective equipment. Inspect equipment regularly and avoid overloading circuits. Grounding is essential for safety, providing a safe path for fault currents. Electrical codes and regulations offer further guidelines, and regular training is necessary for those working with electricity. The DC generator operation relies on electromagnetic induction, where a rotating armature within a magnetic field induces a voltage converted to direct current by a commutator. These generators are used in various applications, and voltage control is achieved by adjusting armature speed or magnetic field strength. Emphasizing the importance of understanding grounding and bonding, connecting equipment and systems to the earth provides a low resistance path for fault currents, preventing electric shock and reducing fire risks by preventing static build-up and managing electrical noise. Different grounding systems exist, including equipment and system grounding, with bonding ensuring conductivity between metal parts. Compliance with the National Electrical Code is essential for safe electrical installations. Additional aspects of electrical safety include preventing arc flashes, dangerous explosions caused by faults, and electrical fires, often due to overloaded circuits or damaged equipment. Following safe work practices, wearing proper protective gear, and regular inspections are critical. Electrical safety training is vital for all workers in the field, ensuring everyone understands hazards, safety procedures, and the use of protective equipment. Chassis grounding, connecting the generator's metal frame to the earth, protects against electric shock by providing a path for fault currents. Adhering to manufacturer instructions and National Electrical Code requirements ensures proper grounding and prevents electrical hazards. Consulting with qualified professionals is always advisable for specific safety concerns.